Hello and welcome to the 10th lecture in 22nd chapter of our comprehensive course on AI, ML and DS. Now here we want to talk about this thing, that is uh, model creation, training and validation. This part of our data science life cycle. Okay, because in previous lectures we already talked about two models, in fact three models: random forest, XGBoost and Lasso. But at that time our purpose of creating this model was just getting feature selection or finding what are the most important features which affect the response variable. So we did not bother about how accurate our models are, and we chose some algorithms like XGBoost or random forest which have a special feature speciality that as a part of that training process the feature importance is built in. So the feature importance plot was obtained and we found the top 5 features or top 4 features depending upon our requirement. Now here we want to do model evaluation. So now we will not only create the model, but once the model is created, we will validate the model also. Validating the model means what? So it is this process. We start our process this way, that we know that there is one full data set. We divide it into two parts. One part is called this white portion, that is called feature matrix, and another part is this purple portion which is called response vector. Then each of that part is further horizontally splitted by this kind of dotted line, say 70% above the dotted line and 30% below the dotted line, so that the feature matrix X is converted into X train and X test Y portions, and the response vector Y is divided into Y train and Y test, two purple portions. If required, we scale this two Y portions, that is X train and X Y train. Okay, sorry, this X train and this that is the scaling is always done with X train and X test. So that is only the features are scaled. Response variable is not scaled. So this is X train and this is X test, and they are scaled and if required. And then we use only the training portion, upper portion, for model training. What is the meaning? We expose our model, whichever model which we are using, say random forest or XGBoost or Lasso, whatever model. We expose our model to the 70% of the training data, including the labels. Labels means the corresponding values of the response variable, right? So the model learns some patterns, that for these values of features, this is the response variable. For this some other values of features, this is the response variable. The upper diagram would be pattern. Okay, that is, say first row gives some values of features, and first yellow row that gives corresponding response variable or label. The next row, that is another some values of features, and this is corresponding label or response variable value, and so on. So we go on doing this all features and their response variables one by one, right? And once it is done, then what we do is, our model, once it has seen entire training set and the corresponding response variable, that is the upper portion, then we say that it has learned some patterns, and such a model is called trained model. Now the question arises is what to do with that trained model. One application we have already done earlier, that trained model can help us to know feature selection, feature importance. But that trained or fitted model, more important use is to make predictions. Now what is the meaning of making prediction? Then this is our trained model, same here, that is the same trained model. We feed that trained model with this much part. That is what we are feeding now, X test. We are not feeding Y test. So that means the corresponding labels are hidden from this training model. So we just feed the features for the remaining 30% of the rows. And based on the values of those features, this training model finds the corresponding label values. If this is regression problem, then it will find the corresponding numbers. Say if it is asked to predict the salary for those 30% observations, then it will predict the salary of those 30% observation. Maybe their 30% is 3,000 rows. Then for each of the row, it will predict the salary. That is called regression. Or if it is asked to predict the class, that whether the patient will be diabetic or non-diabetic, like that, or whether the customer will churn or not, yes or no, then it will predict the probability, or it will predict the outcome, yes or no. Okay, but this is what is the predicted labels. So these labels are created by the trained models by using only this white portion, that is X test, and without any help of this Y test. Okay, so that means this Y test is not used. So that is why this is called Y predicted, and you can see color is also kept different. So this Y test is purple, while Y predicted by the models using this white portion X test, that is shown by pink. Now how accurate your model is, that is decided by this parameter, this comparison of this y test original levels and y test predicted levels, and the difference between those predicted and actual value. And we know how to find the difference. We can find the mode of the difference, or we can find the sum of squared error, that is predicted minus actual uh, in a parenthesis whole square. For every observation we do predicted minus actual square, predicted minus actual square for all these 30% of the observation, 3000 rows suppose they are. Then we do sum sigma predicted minus actual square, and we try to adjust certain things in our model that sum of squared error is minimal. And when that sum of squared error is minimal, then we say that it is the best trained model, right? So among several models which you have trained, the one which gives minimum sum of squared error between actual levels of y test and the predicted values of y test, that gives the best possible model. And then you can even quantify also that best possible is how much. So for that, you what you can do is you can we have defined certain quantities like r square or mean squared error or root mean squared error and all those things. So when you find those quantities and you ensure that those quantities come within the acceptable limit, for example, you earlier decided that r square should be above 90% or 0.9, and you got r square is equal to 0.91. So then you will say that your model is validated. Similarly, suppose you have decided that your root mean squared error is, say, it should be less than 5%, and suppose you got root mean squared error is 3.89%. So you will say that yes, my model is validated because it gives error less than the acceptable limit which I had decided in the beginning. So for validating a model, you have to make predictions on the unknown data. Unknown, I am saying this is unknown because while training, while the model algorithm was learning pattern, at that time it was only exposed to this. It was never exposed to this thing. So that means these observations are unknown for my this trained model also. And while I make the trained model to make predictions on the unknown data and measure certain metrics, this process is called model validation. And this making predictions on the unknown values of features to get the corresponding value of the response variable, that process is called prediction. Okay. So now we want to learn about what is this techniques used for model evaluation and validation. So I hope that I have made myself clear. Okay, that what is this part all about. Now this part has these many topics. One, introduction to model evaluation and validation, common metrics which are used for model and evaluation. But we will only talk about regression problems, that is predicting the values of some continuous variable, like predict the salary or predict the maybe sales of a company, or predict number of number of employees who are likely to, or predict number of customers who will buy, respond to given marketing campaign positively, and so on. So that is what is called regression. Now for regression, we are not talking about the metrics for classification, whether or not person has cancer or not, or diabetes or not, whether or not customer will churn, whether or not employee will churn, that is employee will leave your company and go to other company. All those type of problems have different metrics. We are not talking about them. We will talk about them when we learn classification. So for regression, mean squared error, root mean squared error, mean absolute error, these three are important parameters. Then r squared is one important parameter. And then the question is how to find these parameters. Then what is the process? How to do this? Then for that, techniques for model validation, that train test split, cross validation, and then some code examples for this model validation. So first part is introduction to model evaluation and validation. Model evaluation and validation are critical steps in the development of machine learning models. They help determine how well a model performs and whether it generalizes effectively to a new unseen data or not. Okay, because I said that thing that when you are comparing the predictions on this data, that are predictions made on unknown or unseen data, with the actual results for that unknown data which you already had, but you did not expose those things to your machine learning model while it was getting trained. So that these two can be compared, predicted value and the actual value. So that is called evaluation process, right? So it involves what are common metrics. Then one is mean squared error. Mean squared error is this it measures the average of squares of the error, that is average squared difference between estimated value and actual value. So now I have to take some explanation of that. Of course, the explanation is very simple, and as such, in a scattered manner, we have done that explanation here and there many times, but now at one place. Okay. Okay. So this is what a simple linear regression example that we are taking, and suppose these are 4 data points. this is the actual data point which are shown by brown color, and the corresponding predicted values, they are on this dotted blue colored line, that is the line of best fit, and they are shown by red colored or brown around which there is a red ring. Okay, so all predicted values will be on the line of prediction, that is clear. So that is the line of best fit. Okay, and all the actual data points, they are scattered everywhere around this line, but a rough linear trend is there, and only 4 are shown as a representative number, but actually there may be 40,000 or somewhat that kind of data set, and all those data points, they may be spread around this line in maybe this much region, right? So this region in which all those brown colored points are there, and their corresponding predicted values are on this blue dotted line, that is the line of fit. So y1 is this one is first point, and its actual value is y1, which is shown by this black colored this cursive bracket. Okay, and its predicted value is yp1, or just it is shown by y1 with a hat like symbol. So that is also another way of showing predicted. That is on this line, this red colored dot, and its value is y1 hat. Okay, and therefore this difference, that is y1 minus y1 hat minus y1, or y1 minus y1 hat, whatever you want to talk it. But that if I see the difference between predicted and actual value, then this will be y1 hat is a smaller number, and y1 is this whole bigger number, and therefore y1 hat minus y1, this would be a negative number. So this would be negative. So that is okay. Similarly, second point is below the blue color line, so for which the actual value will be only small height from the x-axis, and the predicted value, that is the red point height, that will be larger height, and this difference, only difference is shown this time, is y2 hat, y2 predicted bigger height minus y2, that is the smaller height, right? So that is this time positive. So suppose for the positive, I am writing like this, that this is positive, red color, and for negative, I am writing green color. Okay, so this is positive. Okay, then for y3, third point is this, and for which actual height is more, that is like this from the x-axis this. So that is the actual value of y3, and its predicted value of y3 is y3 hat, which will have less height. And suppose I do y3 hat minus y3, that is this much height minus this whole height. So obviously the answer would be negative, and therefore that I will have to take to the green color. Okay, and this is again a point below the line, and therefore this is actual y4 smaller height, and this is y4 predicted. Predicted points are on the line of prediction always. So this is y4 predicted, and therefore y4 predicted minus y4, that gives me the line of that gives me the difference or the error. And in this case, predicted value is more than actual value, so that means this would go, that is difference would be positive. So the difference between predicted and actual value, that gives error. But if the point is above the line of fit, so for those type of points, the error would be negative, and if the point is below the line of fit, like this point 2 number or 4 number point, so for that the error would be positive. And remember, there are not 4 points, but say n point, where n is equal to 10,000, or all these points are spread in this big green colored bubble, right? So then how to find the error? Because one problem you can immediately see is that if I directly add the errors, then I will get less estimation of error, because certain positive values will cancel out certain negative errors, and therefore overall error will appear to be less than what actually it is in each observation's prediction, right? So what is the way out? There are two way out of that. One is that instead of considering positive and negative, you just consider the mode of them. So mode means you consider that each of these is put in modulus, and therefore positive will remain positive and negative will remain negative. So that is what this is. That is predicted value minus actual value, but in a mode. And then you have to write it, this sigma, this much I is equal to 1 to n, where n is the number of data points. So for all the data points, not only for one, but for all the data points, you find the difference between predicted value and the actual value, and take the mode of that difference, absolute value, don't take negative, then that parameter, and then sum all that. Sigma means summation, so addition. So y1 minus y1 predicted minus y1, y2 predicted minus y2, y3 predicted minus y3, and so on up to yn predicted minus yn, and then do the sum of all those things, right? So if you do the sum of all those things, then that thing is called the mean absolute error, mean value of absolute error. That is called mean value of absolute error, right? Now, that is one way of solving that problem of some positive error and some negative error. Other way of solving that problem of some positive and some negative error would be first square each. So negative square, that is all these green terms, their square will be positive, and positive square, all these red terms, their square will also be positive. So as a result of that, the whole thing will become positive. So that is called mean squared error. So again, what it will be? Y1 predicted minus y1 whole square plus y2 predicted minus y2 whole square plus y3 predicted minus y3 whole square plus y4 predicted minus y4 whole square dot 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 and so on up to yn predicted minus yn whole square, right? And then sum of all those terms. So if you do sum positive of all such terms, then that will give me mean squared error. And there is, as such, my problem is solved because the square is always positive. But one problem with this is, suppose this y quantity which is being measured or being predicted is salary in dollar. Okay, so this mean square error, that will come in dollar square. Okay, it will be in the square of dollar. Now that means I cannot just write plus or minus this many dollar, whatever my prediction is. Suppose I get that the predicted salary for one particular employee is $10,000, but then I have to write plus or minus certain error, right? So the problem is this error is there, but this error is in the dollar square. So I can just take a simple solution that mean squared error is put in the square root. So that phenomenon, that quantity is called root mean squared error. So root mean squared error is nothing but sigma is equal to 1 to n y predicted minus y whole square, right? That is the mean squared error put in a square root. And the advantage is that its unit is the same as the unit of predicted quantity. So if your root mean squared error is 5% or 5 by 100, then of original value, that is, then in that case you can, or suppose you found that 5% translates to $300. So then in that case you can write your answer in 10,000 plus or minus $300. So that means your actual prediction may be actually $9,700 on the lower side. Actual salary may be this, you are predicting 10,000, or on the higher side it may be $10,300, right? So you get your answer in an interval, that your predicted salary is within this interval, and we know that it can be given, such answers can be given with certain confidence levels. Okay, so this is about the three kinds of error. Now let us do that. And yeah, mean squared error measures the average of squares of the error, that is average square difference between estimated value, and estimated means predicted value, and the actual value. Root mean squared error is root of the mean MSE, root of mean squared error, square root, take its square root, and provides the error metric in the same unit as the unit of response variable. And then third is mean absolute error, that is, it measures the average magnitude of error in a set of prediction without considering their direction. So that means whether this whole thing is itself error, right? Y predicted minus y, difference between predicted value and actual value, difference between this pink values, that is the predicted values, and these purple values, which are the actual values for the test observations. That difference will give an idea about the error, but without considering their direction. Direction means whether they are positive or negative, that is ignored by putting them in a bracket. So these three quantities are related, and they can be easily remembered, their definition, from this simple diagram, right? But fourth quantity, that is R square, that is called coefficient of determination, and that is a slightly different way, that different thing. So it provides an indication of goodness of fit. So that means I say that I can take several lines which pass through my given set of data points. Okay, so suppose there are 10,000 data points here in this green region. Now one person has taken this green line, and another person has taken this green one was this blue dotted line, and another person takes that no, from through all those data points, this red line is called line of regression, or line passing through the line giving the predicted values. So now the question is, whose line is better? So the line which gives the minimum value of those parameters, these parameters, MSE, RMSE, and mean absolute error, that line is the best. So suppose this dotted blue line, that is the line for which mean squared error, root mean squared error, and mean absolute error is the minimum. So then I will remove all such other other lines, because I can draw infinite number of lines theoretically passing through various data points, but I can remove the other lines and keep only the line of best fit. So now only the line of best fit is kept, and now I can define a quantity which explains, which defines, or which measures how much variations in the samples is captured by my line of best fit, or that means a measure of how unseen samples are likely to be predicted by the model through the proportion of variance explained. So what is the meaning? That red line which I had drawn, suppose it can explain 85% of my variance in the data set. What is variance that we have done? It is a quantity which is obtained by deciding how far away the data points are spread with respect to mean or median, right? That is, we said that if there are two bell curves, one bell curve is like this, thin and tall bell curve, and another bell curve is like this, wide and short in height, then the red one has less variance and the blue one has more variance. But this is for two different data altogether. Now suppose I have one data only, say only the blue data. So that means this is my data distribution, and let us assume that it is, follows the normal distribution perfectly. Now it has a certain variance, that is with respect to its mean. With respect to the mean, for normal distribution, the mean, median, mode, they are at same point, and they pass through the peak of the bell curve, right? So then that means the line passing through the mean, median, and mode, that passes through the peak of the bell curve, symmetric. Okay, so now this much is the variance at every point. At this point, how much is the variance? Then it is the square of standard deviation at that point, the square of standard deviation at that point, the square of standard deviation at this point, the square of standard deviation at this point, right? Now the question is that how much I make two models for explaining my this data. Then one model can explain 95% of the variance, and another model can explain only 80% or 83% of the variance. Then obviously the model which explains it 95% of the variance, that model is the best model, right? Now you must have some quantity which can measure what proportion of variance is explained by a given line of fit. So if there are two different lines of fit, the one is this, that blue dotted line, and it explains 95% variance, and another is that red line which I have now deleted, but that explains only 83% of the variance. Then we will say that the R square with this blue dotted line is more, 0.95, and the R square with that red line which I have deleted because it gave more errors. I have to choose the line which gives minimum value of MSE, RMSE, and MAE, right? So that line was that blue dotted line, and it gave me R square 0.95. So then I can say that that value of R square is the best possible value because I can explain 95% of the variance in my data set. Okay, so regression quality is always measured by this R square. Okay, fine. Now here, these are the techniques for model validation. So train test split is involving the splitting of the data. This is not a train test split. This is the whole data set with features and the response variable. And when I just color out one column purple, that means that I have just made feature matrix white colored separate and the response vector purple colored separate. So that means X and Y, capital X and small y, they are separated. But now I make a division split like this, so that X, that is the white colored portion, feature matrix, is divided into upper part X train, lower part X test. So if total 10,000 rows are there, then this X train may have 7,000 rows and X test would have 3,000 rows, like that. And similarly, this is Y train and Y test. 7,000 observations of predicted response variables are in Y train, and 3,000 values of response variables are in Y test. So that is called train test split, which I have done here. Okay, so when this split is completed, now I get this kind of situation, train test split. Okay, and that is one technique for model validation. And important thing, why it is important thing, why it validates the model? Because the real validation of the model is how it performs on the unknown data. So if you don't do this splitting and you train your model on entire this data set, this whole data set, then your model during training has seen this values of labels for the test sample also, and therefore when it tries to predict the values, then it is very likely that it will predict the values which are nearer and nearer to the seen values, because it learns the pattern. So we do this splitting so that the entire training process is done on totally different rows, 7,000 rows, and the testing process is done on totally different rows, that is this many rows, 3,000 rows. And even in 3,000 rows, while testing, we just expose the model, train the model, which was trained using both X train and Y train, that is red and white and purple part. But during testing, we expose it to only the white part, that is X test, and it makes its prediction, right? And whatever predictions are made, we compare it. When I say compare, all those terms should be come in mind. That compare means how? Then by MSE, RMSE, or MAE. So when you compare the predicted values, Y hat values with Y, then you get the evaluation matrix, right? So train test split is important because it is the prediction made on unseen data. That is the real test of any machine learning model. And similarly, there is another technique called cross validation. Now we have done some discussion on that cross validation also, so that we know what is cross validation. Still, just as a quick revision, so just like in 19th chapter, we had talked about this train test split by this diagram, we also talked about cross validation using this diagram, right? So when you do the train test split, At that time you can do one thing, that you can take multiple folds in your data. So that means suppose there are total 1000 observations, then you divide it into 5 folds of 200 rows, right? And in first thing you take the top 200 as the test set and the remaining 900, remaining 800 as the train set. So top is suppose fold 1, then fold 1 is my test set, and the remaining are suppose 200, another 200, another 200, and another 200. So those 4 folds, they are folds 1, 2, 3, 4, 5, right? And then next time you do this split 2, and at that time you take a train set as fold 1, okay, and test set as fold 1 and fold 3, 4, and 5. So 1, 3, 4, and 5. These are taken as the folds. And test set is the second fold which you want to do. Then in third split, you have to do train set is equal to first, second, fourth, and fifth. And third fold, that is in between central 200 rows, they are your test set. Then in split 4, you take a fourth fold as your test set, and first, second, third, and fifth. First, second, third, and fifth set of 200 rows, they are taken as train set. And in last, you take top 4 folds of 200 rows each as your train set, and the last set is called test set. So ultimately, you are doing train test split only, but this makes the process more robust. Why? Because from same data set, you are making train test split 5 times instead of just 1 time. Otherwise, you could have done simply the top are train 800 and the bottom are test. But we may not learn some pattern from the bottom 200 rows, okay? Or we may learn some pattern excessively from the top 800 rows. So here we are giving chance to every row, every set of 200 rows by training and testing 5 times. So this becomes one train set and top 200 one test set, and first model training is done. Its performance metrics like RMSE, MSE, and MAE are calculated. This becomes the second iteration. At that time, the second set of 200 rows are taken as the test, others are taken as train, and again training is done, and then testing is done, and MSE, RMSE, and MAE are calculated. So that all performance metrics which are calculated 5 times, their average performance matrix is presented to you as the final matrix. This process is called 5-fold cross-validation, because you are dividing your trained data into 5 splits or 5 groups, each of equal size, right? Instead of that, you can make 10-fold cross-validation also. But this cross-validation is another technique for model validation, because it often prevents data leakage, it prevents overfitting, and it makes the model more robust and more generalizable. So with this much background, we will do in next lecture some code examples, and then we will continue with part E also, introduction to sklearn library. Or let me finish this code example here only, because it is very, very small example, right? So then this much is importing the required libraries. So import and execute that cell, okay? Then now I will remove these lines. I have already included them. This is generating some synthetic data and creating the train test split. So each of these I will put in different cells. So generate synthetic data and this, and then do the train test split. That much I am putting in other. And even this generate synthetic data also, I am showing that data here in this cell. So I am showing that in this particular cell, okay, what synthetic data we have generated. So X is this, and since we have kept things simple, only one column, number of features is equal to 1, okay, and these are the values, 100 observations are there, and this is my independent variable. Now what is the corresponding value of dependent variable? Then the corresponding value of dependent variable is this y, and that are 100 again values for predicted variable or labels for my independent variable. So this y is my dependent variable values. So as I will need these all space, I don't want to scroll, I'm clearing it, because these are just x and y. Now you have clear idea that x is 100 values of independent variable and y is 100 values of dependent variable. Now this for simplicity, you can just plot a scatter plot. And earlier in the scatter plot plotting that you have done, we used to do so many steps. But you should understand that when you are doing just a quick and dirty analysis, at that time all those steps are not required. They are required only for extra frills. Otherwise, just write plt.scatter x, y, where plt library, that is matplotlib.pyplot as plt, you already imported earlier in this Jupyter session. So fine, if you are not imported, then import that, okay. And then before this, we used to do several steps like plt.figure. Inside we used to write fig size is equal to 10, 8. Then plt. scatter and x, y. Here also we used to write maybe color is equal to these, and the shape of the points, instead of circle we want to plot something, background you want to adjust. But these are all extra frills. If you want to do then plt dot x label for x axis label, plt dot y label, plt dot title, plt dot grid. Grid is equal to true will plot lines like this, grid lines, okay? But all those are extra fields. Actually, there is only a single line, plt dot scatter, x and y. And if you just do that, then at least for quick and dirty analysis, this is fine. That it shows that my y increases roughly linearly with x. And since I added some noise, that is why the increase is not perfectly on a straight line, but it is slightly jittered with respect to the straight line, right? Now I'm doing train test split. That means I'm doing now this process. I'm already here. My x and y are separate, but I now want to do this. From this, I want to go to this. So we use train test split. X and y are separate. Test size I am keeping 0.2. So out of 100 samples, 20 samples will go in the test set and 80 samples will go in the train set. Okay, and I am saving them in the 4 standard sets. So that is done. Now once that, this is again the same step just being repeated. Okay, now I will print them. So print them, and you can see that this is my X train, 80 rows. These are the corresponding labels of, sorry, this is my X test, the last 20 rows. This is my Y train, that is the corresponding labels for those 80 rows of X trains, and this is my Y test. Okay, again this cell also, this output I am deleting because I don't want to scroll up and down a lot. Okay, now train the model. Earlier we imported that library. So from sklearn linear model, import linear regression. So create a linear regression object and fit that object on X train and Y train. We know that if you have scaled, then here you will write X train scaled. Okay, so you are fitting your model. So that means what you have done in this diagram, you have come to this point. Now you have a trained or fitted model. Okay, and this sklearn is so good that once it has fitted its model, then it will show here 2 legends. One, it shows here fitted. Okay, and another, it shows here documentation for linear regression, and you can just click on it and you will get entire documentation of linear regression algorithm and various examples also, code examples also. So everything you need to know for linear regression is here. Okay, internet must be on, but that is how usually people do coding. Okay, in the industry, that means it is not expected that one remembers everything. Of course, after prolonged experience, you will automatically remember. That is a different thing. But sometimes when a special edge case comes, in which you need to refer the documentation, then refer the documentation. There is nothing, no shame in that. Okay, now predict. So now I am doing what? I am doing, if I show this diagram, now I have my trained model, fitted model, these or these. Now I am trying to expose my fitted model to only X test, or only X test means only this part, right? Green, lower green. And I am trying to find Y predicted. So that is, I am trying to find this, not Y test. Y test is nowhere involved during the this process of prediction making. And once the predictions are made, then I will compare it with this Y test. For comparing also, what are the parameters which are used for comparing? That we know that are these parameters, mean squared error and R root mean squared error and mean absolute error. But you don't need to actually draw some diagram and find each observation difference between predicted and actual value, then square it, then take sigma of it. All those things are automatically handled by Python. You just import this library from sklearn.matrix, import mean squared error and R square. So once you predict, let us first make prediction. So model.predict, model is my trained model, fitted model, and predict is X test. So on this, only this, I am testing by making the prediction, and at that time I am hiding this portion so that labels are not known, means this is as good as unknown data, right? Okay, and I am predicting, and once predictions are made, actual values of those Y is already with me. Okay, so I can compare my predictions with Y test, that is actual values of labels. It was already with me, but I did not use them for prediction because I wanted to simulate a prediction on unknown data, right? So I have to use the functions which I imported, or the facilities which I imported from sklearn.matrix, import mean squared error and R square. So mean underscore squared underscore error, first argument is Y test, which I had hidden from my model during prediction, and second argument is the predictions which I got. So that will give me mean squared error this much, which looks to be pretty good enough, I would say, and R square comes out to be 80%, which is also fairly good enough for a randomly generated data. 80% of the variance can be explained, right? This is the explanation of the code, but that I have already done. Now in this only, I can do 5-fold cross-validation and print a cross-validated score. I have already trained a model, so I don't need to train model. This is important thing which you must remember, that mostly what we do is during this training and prediction, training only, we do the cross-validation. Later on, in most of the chapters, we'll do like that. But suppose you have not done cross-validation earlier, then this whole training and prediction was done without cross-validation, but you already have a fitted model. So that fitted model you have to use and for cross validation. So import numpy and cross validation score is equal to cross underscore validation underscore score. From where that function is there, that also you have imported. That is here from sklearn.model selection import train test split and cross validation score. Okay, that is why these two are always imported together. So as I said, mostly what we will do is with train test split and the training process itself, we will include cross validation inside. But how? At present, don't worry. So at present, suppose we forgot to do cross validation. So we are doing cross validation here with our trained model, fitted model, and again taking x and y only. I have to specify CV is equal to 5, and I have to specify some metric for scoring. Negative mean squared error. Okay, and then I print those scores. Okay, sorry, this is for CV scores. I'm scoring on the basis of negative mean squared error, and next time CV R2 scores, that is R square score. Again, I'm using cross validation scores. Again, model train model X Y CV is equal to 5, but this time my matrix is R square. Okay, R2 is written, but it is R square, right? So then print those two. That will give me that cross validated mean squared error is less. That you can see the advantage of cross validation. That when you use 5-fold, when you did not use, it was 416. When you use 5-fold cross validation, it reduces and it became 325, right? So your model has become more robust and generalizable also. And R square was 0.80 earlier, 80%, but now after cross validation, R square has become 83.7% or nearly 84%. So these are the advantages of various model evaluation and validation techniques. We have done this part, and now we will do only this last part is left, introduction to sklearn library. Thank you, and we'll see in the next lecture.